This is our simulation. It is trying to find the fastest path to get from point A to point B without smashing into anything. The yellow cylinders are the obstacles. Now, here's the cool part. This whole process is inspired by the hunting strategies of gray wolves. This method is what the smart folks call gray wolf optimization. We are exploring how these wolfish tactics could solve some pretty tricky engineering problems. It sounds interesting to me. I hope it is interesting to you as well. The math behind it is actually pretty simple. There are just a few simple equations to mimic what wolves do in the wild. Sure, it might look a bit overwhelming at first glance, but it's mostly just a bit of copy-paste with those equations. Let's rewind to 2014, when some researchers had an aha moment. They noticed that wolf packs had a strict social hierarchy. Alpha the boss, beta the right hand, delta the caretakers or scouts or elders, and then omega. No one cares about omega. So when we talk about optimizing things, we're basically mapping this wolf hierarchy onto our potential solutions. The alpha is our champion, beta is the runner-up, and delta is our bronze medalist. The rest is just omegas, trying to keep up. Now let's talk about objective functions. This is the function that tells us what we are aiming for. Usually, we want to either minimize or maximize this function. For example, in our drone simulation, the goal is to find the shortest path that avoids obstacles. So we want to minimize the path length and the collision vector. But we'll discuss this term later. Before we get too deep into this, we start with a simpler example. Imagine you've got this example objective function. I know it's complicated, but there's a reason why I chose it. Trust me. We plot this function into a 3D plot. Every point is a potential solution, and the height shows how good it is. Since we want to minimize this function, the lower the better. Now you see some red crosses. Those are local minima, or spots that seem great if you're not looking too far. But there's only one blue cross, marking the global minimum. That's the best solution we want. Here's the kicker. We don't know exactly where that global minimum is. I can mark them here because I cheated. I used some other numerical tricks. But that's beside the point. Plus, there are all these suboptimal solutions trying to lure us away from the best one. So, how does our algorithm deal with this? Well, the omegas, our not-so-good solutions, start moving based on where the alphas, betas, and deltas are hanging out. It's like they're following the lead of the best hunters. But if we just follow this strategy, we might converge too fast to a not-so-good solution. It's like a wolf settling in for a rabbit when there's a nice, juicy deer just around the corner. That's where we sprinkle in a little randomness, especially early on. This randomness is inspired by the way wolves encircle their prey. They don't just rush it. They take their time, surround the target, and close in slowly. Similarly, in our algorithm, the randomness starts high and gradually decreases as the wolves, our solutions, focus on their target. Now let's zoom out and see how this looks from above in 2 dimensions. This is our forest. Imagine we scatter our wolves, aka potential solutions, across this forest. We then evaluate where each wolf stands using our objective function. The top 3 solutions become our alpha, beta, and delta, and the rest of the pack, the omegas, adjust their positions based on these leaders. And don't forget, we keep some randomness in the mix to avoid jumping to conclusions too soon. Over time, this randomness fades away as the wolves close in on their prey. Of course, there's always the chance of getting stuck in a less than ideal solution. That's why we need just the right number of wolves and enough iterations to improve the simulation. So let's take this method and apply it to our drone path planning problem. Each wolf now represents a full path from start to finish. Each path is made up of waypoints connected by straight lines. The objective function here is simple. Minimize the path length and avoid obstacles. For the obstacle avoidance part, the collision factor, we use a simple trick. If any part of a path touches an obstacle, we punish it with a high score. Basically, if there's a collision, it's a big no-no, so C equals 1. And if there's no collision, C equals 0. Here's how the simulation plays out. Let's say 5 paths with 3 waypoints each. We evaluate them and pick the top 3 as our alpha, beta, and delta. In each iteration, we tweak the waypoints of every path based on our leader's waypoints. So point 1 follows point 1, point 2 to point 2, and point 3 to point 3. We also throw in some randomness to make sure we are not missing out on better solutions. Now watch this path evolve. They start pretty chaotic, crashing into obstacles left and right, but gradually they converge to a shorter and obstacle-free path. After enough iterations, our alpha path becomes the winner. Making this into 3D is no big deal, we just add another dimension to our equations. Now, our drones can dodge obstacles by flying over or under them too. So next time, don't ignore your biologist friend anymore. Ask them about animal behavior. And when they ask why, just say, I'm trying to make my drones fly better.